going on, Mistral? And Cameron. What's up, guys? And Sib. Okay, so I'm sure some of you guys saw last night, I did post the grades for Exam 2. Was better than Exam 1, for sure. I think the average was around like an 80, 82, compared to, I think, Exam 1 was like a 78, so you guys did better, which is good. Albert is finishing up typing up the solutions guide, and he said he'll have that to me later tonight, so I will post that, and then once I do, you guys can start sending in like regrade requests. If you already see something that's wrong, for instance, Kudu marked your answer completely wrong, but you have the right answer, I don't know, in like a screenshot on Kudu, or like you also have it on your supporting work, you can email me about that like right away. I think I've ironed out, there were a lot of like little technical bugs, because some of you guys don't use the same email as you do on Kudu as you do on like UCLA. So I have to tell ChatGPT to try to match by like names, but then some of your names don't match up either, because you all got like nicknames or like fun names. So then I try to do it by ID, but then some people don't have an ID. So there's always one or two that like slips through the cracks. So if you see something wrong on Brew and Learn with your exam grade, like if it just shows all zeros, or if like you didn't get credit for questions, you can email me about that now. But otherwise, yeah, regrade requests. Let's wait for Albert to give me the solutions guide, and I'll post it. And then you can go through that and do the usual, you know, a lot of you guys did a really good job of, you know, showing me what your work was, and then like kind of highlighting like, hey, this is what I did wrong, and you know, it should have been this, and then like I would have got the right answer here, and then that error carried through. Like, I love that. Yeah, that's great. That makes it very easy for me to like award extra partial credit. Some people were like, can I get more credit for 10? And I'm like, bro, what? Don't just tell me in an email, can I get more credit? You gotta explain to me why. And like, I really prefer if you like show me in the email like where the document, because if I have to go like hunt into Gradescope to go find your work and stuff, I'm less likely to be like generous. So a lot of you guys did an excellent job. I really appreciate it. Thank you for putting in the time. But I'll make an announcement about that later tonight, and that'll probably be due by Friday, is what I'll say. I'll say like regrade requests are due by Friday night. I know you have the final on Friday, so you know, try to get the regrades done Wednesday or Thursday. The requests. Sure. Yeah, if you're off by rounding, that's a perfect example. Yeah, just show to me. Be like, hey, I was off by rounding here. That's cool. Whatever. I'll give you like, you know, -1, -2 or something. Versus, in general, I usually just give like half credit if you did something. If you did something that looks like it's correct, you get half credit. That's the points for trying. But if it was something even smaller, again, I don't have enough time with a summer course to go through everybody's work and find out like where the individual errors are. But if you did something smaller and you let me know, then I can give you a little bit more credit for that. Also, it's a great activity for you because you get to learn more by learning from your mistakes. So If it's very valuable, and I tell this to students regardless, if there's even the opportunity for more extra credit, for more partial credit, you should always go through your old exams, see what you got wrong, and see why you got what you got wrong. And that'll help you do things better in the future, especially on the final. So yeah, I will make an announcement on Brew and Learn about that once I have the solutions from Albert. Again, probably later tonight. But you should have a rough estimate of your exam grade so far on Brew and Learn. I was up kind of late, like getting that set up. So check that. Should be good. What else do we got? Oh, yes, the set surveys. Yeah. Okay, cool. Yeah, let's check what the percentage is at. That closed this morning, so I really hope everyone did it last night. I sent out another announcement on Brew and Learn to really try to encourage people, and I appreciate you guys on Campus Wire also trying to corral your other fellow students to do it, because it helps everybody, And this class is not curved, is what I say. So everybody's grade goes up. So you're not hurting yourself by helping your friends. Okay, let's see what we're at. Looks like survey says, wait, where's my office hours? Okay, let me paste this in. Ooh, okay. 85%, nice.
That's dope.
Good job, guys. 85%, nice. Really good. That's really great. Yes, bang. There you go. Yeah, you guys made it over the 80 percentile. Yeah, nice. I wish I could see how as a function of time how this went up, because yeah, it was at 60% yesterday, and I was like, oh man, I don't know if they're gonna make it, but you guys did it. Yeah, congratulations. Yeah, good job. So yeah, everyone will get bonus points on their final grade. Which, yeah, speaking of, this is the last clicker that's due for the course. Last clicker is today. And then your last homework is due tomorrow at 2 p.m. After that, all grades are basically finalized. And I will work the daunting task of migrating everything from Kudu into Brew and Learn. Probably Wednesday night, Thursday morning, afternoon-ish. So hopefully by Thursday night, I know it's the night before the final, but again, they don't really give me much time here. You should see all of your grades, including the bonus credit here. If you have the certain levels on Campus Wire, I think I'm going to close that off also, probably Thursday I'll close it. So, make sure to participate, be active. Don't go trolling engagement farming posts though. Please don't do that. I had some students my last quarter that just started posting pictures of I don't know, seals and walruses. And they're like this upvote for credit. I'm like, don't do that. Y'all realize I see what goes on in Campus Wire, right? But yeah, if you have any other questions about physics, this is a great time to ask, right? Because it's before the final, and also it's a great time to answer, because then your answers get upvoted. You'll notice I go in and just start upvoting people too. If you're participating and doing good stuff, I'll give you upvotes, and that will also determine more extra credit in the class. Mistral says, should we be reviewing every clicker we ever did? I mean, ideally, yes, but that's a lot, right? Because there's 24 of them at this point. I would say focus the most on clickers and homeworks that were after the last exam. So stuff on circuits with resistors, DC circuits, and then Kirchhoff stuff, and then charging capacitors. Yeah, that's stuff you should really focus on. That's stuff I'll most heavily probably pull from. I say 50% of the final will be over stuff we've done in the last 2 weeks. Are the solutions for the midterm 2 open now? I don't know. I emailed Albert last night, and he said he was working on them, and he said he'd get them to me either sometime today or later tonight or tomorrow. It's okay. Whenever Albert gets them to me, I will make an announcement. Y'all can do your regrades. But right now, you should be able to see your answers on Kudu. You should be able to see what you put and what the correct answer was, and maybe that can kind of help you. But yeah, wait for the official solutions to come out either sometime later tonight or early tomorrow morning, and then you should be able to see what happened. So yeah, I would say the exam is going to be 50% just circuits. Yeah, a lot of circuits. Which I like. I like circuits. Circuits are cool. And we're going to go over some cool ways to measure things in circuits today. So, why are the answers for the clicker questions not displayed on Kudu? Okay. Yes, the reason for this is we like to incentivize students that show up to lecture. If I put the answers in the answer, I know what you're talking about. You're talking about, well, let's see. We probably have a new clicker up already. Let's see what we got. If I refresh. Yeah, you're talking about like how there's like A, B, C, D. Yeah. That is originally done so that we kind of like reward students that show up to lecture and go over it. I understand that it makes it kind of hard to go through the clickers now if you don't have the answers. So you know what I'll do? I will release the document that has the answers for every single clicker. So, because I agree, if you're trying to go back and study the clickers, this is hard because you don't have answer choices, right? So, yeah, thanks. That's a good heads up. I didn't even think about that. Originally, we did this because if we had just put the answers up here, no one would ever show up to class. Or not nobody, but a large percentage of people would just chat GPT whatever the question was and choose the answer choice and be done in like 3 seconds, which, I don't know, it's not good for you as a student because you're not going to learn that way. So we have to like kind of create like small little roadblocks that it makes more sense for you to show up to class. And also, even if you're watching this asynchronously, you still have to kind of watch more of the lecture to figure out like when we do the clickers. So it's like social engineering is all it is. Yeah. Fedekai says, I feel like my processes are probably right, but my answers are way off for some reason. Yeah. Wait, did Albert already post the solutions? Is that what you're saying? I thought he would email me. 1 sec. Albert, if you're watching this. Okay, totally. Yo, that makes sense. And thank you again, Fun Guy, for the feedback. Yeah, no. I totally understand that. And that's my bad. What I should have done is given you guys the answers to the clicker questions, like the document that we have as you're studying. This is the first time I'm hearing about this, right? So, yeah. Always, if something's like annoying or like with the course, please let me know because we all have blind spots. So I didn't even consider the fact that while studying, it would be a huge pain in the ass to have to go back and watch the lectures. And, you know, I'm not expecting everyone to go back and rewatch every lecture in order to study for the exam. Yeah, you should be able to just go through the clickers. So, yes, Fun Guy. Let me put that on my list of things to do. 1 sec. I have a list. There are a lot of things. Oh, it is? Oh, okay. Well, if it's there, awesome. I can't check Brew and Learn right now without like doing the whole login. I gotta go find my phone and stuff. So, if it's there, great. I'll make an announcement about everything here about what we're gonna do with that. But yeah, okay. Let me see. Post clicker answers documents. All right, I will do that for you guys, so it's easier. Okay. Any other questions? This will be the last new content we're gonna do for the class. We're gonna go over ammeters, ohmmeters, and kind of like some more real life electrical hazards and stuff, and like why you don't want to get shocked by things. And then Wednesday and Thursday, I will do a review of what I think are some good, like harder questions that could show up on the final. So it would behoove you to watch Wednesday and Thursday, but I'm not going to put any new material on the exam from what happens on Wednesday and Thursday. So, because I think that's cruel to start introducing new stuff and then you're tested over it like the next day. Like what? That sucks. How much regrade credit can I get for the last 2 questions though? Since I got 50% for each of them, and that's kind of cooked me since I really thought I did everything correctly. If you thought you did everything correctly, Fedekai, go through the solutions and see what you did wrong, okay? And then, again, write a little blurb next to your work showing what you did wrong, and based on that, if it's a small math error that you're making, then yeah, you can get a lot of points back. I'll probably boost it to you get 90% of the credit or something, or I don't know. If it's some bigger conceptual things, then yeah, we don't give as much partial credit. If you completely flat out didn't do anything correctly, then 50% is kind of generous, right? I will tell you, some physics professors are pretty hardcore, and they just give you a 0, and they say no.
No.
So I want to be fair. I want to reward you guys for doing good work, but also I don't want to set unrealistic expectations when you take physics with a professor that's not me, because it can get pretty hardcore, especially in the upper division classes where it's kind of it's all or nothing. If you don't get it right, you're kind of cooked. So I don't want to sugarcoat what the physics experience is. So there's a balance. But yeah. Yes, cool. We'll do a review Wednesday, Thursday. Yes. Go back through some things. Okay. All right, that being said, let's start. Welcome to week 6. Lecture 2, yeah. Last week, third to last lecture. Good. Today we're going to go over, if I can spell this right, ammeters and ohm meters. That's totally cool, Fedekai. Again, go through the solutions and see what was the misunderstanding. That's the best thing for you to do. Okay, so a lot of times we have circuits such as, I'll draw the basic one, right? Let's say we have a voltage source here. We have a resistor here. Let's say this is R1. It's equal to 5 ohms. And then, I don't know, let's say this is 10 volts. We know from Gauss's, not Gauss's law, from Ohm's law, we can describe, for instance, what V1 is. Actually, here, let's put another resistor here. Let me get rid of this one. All right. Let's say this is R2 is equal to 10 ohms. We know from Gauss's law that, not Gauss's law, sorry, for Ohm's law, we can figure out, for instance, what V1 is and what I1 is by doing the circuit analysis that we've done in the last week. But in the real world, we tend to use physical devices to measure these things. And what we do is we will use ammeters and ohm meters. Ammeters measure current, and ohm meters measure resistance. So you can actually measure resistance with these. And I forgot the third one. Voltmeters. Voltimeters. I don't know, whatever. How do they say? And so this measures voltage. Okay? So instead of using math all the time, because you won't sometimes know what all the components are in a circuit that you're dealing with, you'll use a device, which the common one is called a multimeter. I don't know if anyone's ever used one of these before. Let's see. Yeah, you found it more intuitive using devices to obtain results, right? So this is, for instance, this is a multimeter. So this is a device that you see can measure voltage, it can measure resistance, ohms, and it can also measure current. Sophie says my dad has this. Yeah. I mean, I mean, I have one too. I'm not a dad, but it's a very good tool to have if you do anything with electronics. You need to. It'll help you diagnose a ton of things. The souped up version of this, which costs a lot of money. I don't know if any of your dads have this, but it's an oscilloscope. So if this is like a multimeter but on steroids, but these are very expensive. I mean, this is a smaller one for $500. This is also kind of Like, this is really a voltmeter is what it is. Yeah, these are expensive. And then especially if you get into the higher precision ones, bro, look, these can go for $340,000. Yeah, which that's a lot of money. But these are super nice. Yeah. Wow, this is beautiful. You've only seen these in movies? Yeah. So if you might have used kind of an old school one of these before. In a physics lab maybe, or you will when you do a physics lab. These are a little bit more simple, but these are like voltmeters that measure voltage as a function of time. So you can see like time traces of what voltage looks like. And this is useful for AC circuits, which you'll deal with in 1C. Anything that like oscillates with time. A lot of the stuff here we kind of do is steady state, direct current, DC. I guess except for charging capacitors. Charging capacitors does various time, so that you could see on a oscilloscope. But anyways, yeah, this is a more fancy version of a multimeter, and it basically includes a voltmeter in it, and you can configure it to act as an ammeter and a ohmmeter as well. If you ever do physics research, you will use these a lot. I got really comfortable and familiar with using these during grad school. They were, yeah, they're kind of lifesavers for doing any sort of like experimental physics. And they look scary, but they're actually not that bad, and you'll get used to them. So, little preview. But okay, let's talk about like how an ammeter and a voltmeter works. Okay, so the diagram we use for an ammeter. Let me get the picture right here. Is this. Okay. This is an ammeter, okay? An ammeter is represented by, they say like this thing A, and in reality, it's comprised of a couple components. We'll talk about the components. Is this actually feet? Yeah, it is actually feet. Sensation. Sensation, you use a circuit probe, that's cool. Let me get a voltmeter, right, and then this is a voltmeter. And we'll show you how you connect these things. It's actually really cool. Okay. The ohmmeter is a little bit more confusing. I don't think I'm going to go into that. But just for reference, I'll put it here. But yeah, this is a voltmeter. And this right here is an ohmmeter, but don't worry, you don't need to know about this. This is, I mean, even I don't really understand this one. But this is a bit confusing, but we're going to focus on these two mainly. Okay. So, an ammeter works by using what's called a galvanometer. What do they call it? How do I pronounce this? Yeah, galvanometer. Galvanometer. Yeah. So the galvanometer is the G thing here. And then they have what's called a shunt resistor, okay? Shunt is another word for parallel. So if you ever see the word shunt, it's the same thing as like putting, and you should see this, right? This resistor is in parallel with the galvanometer. You may be asking like, wait, what the hell's a galvanometer, right? Okay. A galvanometer is kind of like the old school way of like measuring things. Maybe you've seen like these, for example. This is a galvanometer. You ever seen like some like really old school, meters and stuff? This is an example of one. And so this thing moves back and forth dependent on the amount of current that's running through it. How a galvanometer works is actually a topic for 1C. And let's see, maybe they have a cool little, they have a diagram of it? Oh, they don't. Well, they have a diagram. I wish I had a video of it because it is pretty cool how it moves. But in 1C, you'll learn about how current creates magnetic fields, and those magnetic fields then create torques, and that's what causes a meter here to like kind of move. It's the combination of currents creating magnetic fields, creating forces, which then move the meter. But okay, for our sake and purpose, we're going to say that a galvanometer is just a meter, which looks something like this. And that meter will move back and forth based on the amount of current that's going through it, okay? So this is kind of like an example, and then like they would have like some cool little numbers here, like, well, make it a little thinner. There we go. Like, maybe you've seen them on like old like stereo systems. Yeah, old like hi-fi systems definitely have these. And what they tend to call, they call like this position like full deflection. This is called like full deflection. Which means that the meter is being pushed to its maximum position. And the angle that this thing makes is dependent on current. So we say like this moves to the right with more current. That's how a galvanometer works. Okay. So so an ammeter looks like this, right? And then a voltmeter looks like this. And I'm going to explain why one is like set up in kind of like a series way and why one is set up in like a parallel. There, this is parallel. This is series. Why they're set up. And it has to do with how you connect them. Okay. So the other key thing about a galvanometer is that it measures very small current. So measures very small amounts of current. So, for instance, you can probably see it on this one here. Do you see how it says 20 microamps per division? So that means each one of these divisions, each one of these numbers represents 20 times 10 to the minus 6 amps. So that's a very small number, right? So I guess this has we call this like the full range. The full range is from minus 30 here to plus 30. So that's 60 tick marks, or 60 divisions. So this, at the full reading, will be 60 divisions times 20 microamps per division. So that's 1,200 microamps. Or, what is that? Is that 1.2 milliamps? I'm going to think 10 to the minus 6, 10 to the minus 3. Yeah. So 1,200 microamps, so 1.2 milliamps. So this thing will go all the way to the right at 1.2 milliamps. Oh, I see, but I think this thing maybe has direction to it. Yeah, maybe it measures current in both directions, so maybe it's half that. But in any case, it's a very small amount of current that's needed to move this needle. I don't know if this one is directional. Maybe it is. But again, I'm not going to like test you on that. It's just cool to see like how these things work. So it measures very small amounts of current, and that moves the needle. And then that's how we measure the current going through, we say, like, the galvanometer leg. Okay. Stepping back to big picture, right? How do we use these things to measure current and to measure voltage? Okay. So let's say, for instance, we're trying to measure... Here, let's take our picture here. One second, I'm going to move it. Okay. And then I need this. Oh, no. I hate when it does that. Okay, clear cut power. There we go. Okay. Okay. So to measure current, what we want to do is you want to place an ammeter in series with your circuit. Okay. So to measure current, you want to place ammeter in series with your circuit. And I'll explain like why. So for instance, in our diagram here, right, we know that there's a single current, right, going all the way around the whole thing, right, because things in series have the same current. Okay, so if I want to measure the current of R1 or the current of R2, I just need to measure the current of this like series line. And the way to do that is to pop in this ammeter here in series with the circuit. So what that would look like is we would put like an A here with like a circle, and then we would do a line like that to connect, okay? And then this thing would show some like needle moving, or in today's world, it's a digital display that reads it. And it would tell you how much current is running through R1, which is the same amount of current running through R2 because both of these things are in series. Now, the key thing about ammeters is they have very low resistances. So, ammeters have very low resistance. And we got to think about like why that is, right? If this ammeter had a high resistance, okay, let's say like, I don't know, it was like R was equal to like even like 5 ohms. Let's say it was the same as this. That ends up affecting the total current running through this system, right? Because it's in series. So if we look at, for instance, like I before, right, that would be equal to V over R tote, which would be equal to the 10 volts divided by R tote in this case would be like R1 plus R2 plus the resistance of the ammeter, okay? Now, if this is anywhere close to these numbers, it's going to really change the amount of current that you're measuring. And you don't want to do that. When you go to like measure something, to probe something, you don't want to change the state of what's there, because then you don't know if what you're measuring is real or if what you're measuring is a result of you like poking it. This is actually how like Schrodinger's cat, the whole phenomenon is, right? The cat is dead or the cat is alive. You can never know, because if you try to figure out if the cat is dead or alive, you probably change the state of it. It's a Schrodinger thing, but we're not doing quantum physics. So if the resistance of this is low, right, then you would just measure, oh, cool. I would be like, all right, cool. I before is equal to 10 volts over 15 ohms. So this would be equal to two-thirds of an amp, right? Okay. Now, however, if I have I afterwards, and let's say this ammeter is a really bad ammeter and has high resistance, like 5 ohms is considered high for an ammeter, then this would end up being 10 volts over 20 ohms, right? Because you'd have the 5 from R1, the 10 from R2, and another 5 from the resistance of the ammeter. And so now you would measure half an amp. And so do you see how these are like very different? So very different if R of the R of the ammeter is, you know, kind of like much greater than 0. You want R of the ammeter to be really low, like really close to 0. Okay, but let's think like how does that work in the circuit here? Like how does this ammeter have very low resistance? Okay, so if, again, let's say I have my 10 volt circuit here. And then here I'm going to pull this in. We're going to pull in like what the diagram is. No. And let's say this, right? This is the ammeter being connected. What that is 5 ohms. And this is 2 equals 10 ohms. And this is coming down, okay. Okay, so the ammeter has a couple components, right? So it has the galvanometer, which has its own little internal resistance to it. And then you have what's called like the shunt resistance. And again, this thing, right, gets measured based on like what the current is flowing through it. and you want that to be very small current. So the shunt resistor here, this is usually very low, okay? Very low. And this resistance here is usually very high. And so let's think, right? If you have current trying to flow from here to here, right? It has two paths. It can either go this way or it can go around and go this way. Turns out current always wants to pick the path of least resistance. So if this is very low, more of the current is going to go down in here than is going to go in this direction. Okay, especially if this is a very high resistance. Now this is like not looking as attractive for current to go to travel. And we should remember that, right, from, and this is a good question just to review a little bit from circuits, right? If you have again, let's say you have 10 volts here, and you have two resistors in parallel. Okay. We know that the voltage across both of these things will be 10 volts, right? Because these are in parallel with each other. So this will have 10 volts on it. This will have 10 volts on it. Parallel things have the same voltage. Okay. And then in order to determine the current through it, right? Let's call this like R2, R1, right? We know that I1 is equal to V1 over R. Or we'll just say V over R, V over R1. And then I2 is equal to V over R2, right? This comes from V equals IR. And since they both have the same 10 volts going across them, right? The one with the higher resistance is a lower current. And again, that comes from like V equals IR and just the nature of parallel circuits. Because they have the same voltage, the one with the higher resistance is going to draw less current through it. So in this case, when your shunt resistance is very low, and then we call like your galvanometer resistance is very high, most of the current will go through here, and a small amount of current will go through here, which is what you want. Because remember that the galvanometer usually has a range of like 50 microamps. Okay? So you want to limit the amount of current that is coming into your galvanometer. And also what that does is that does not change the current of the entire system very much. Because, again, if this is a very low resistance and this is very high, then the overall resistance of this thing is also still very low, which means it won't affect the overall current going through. We could see that with here. Let's say, for instance, that, say that like R2 is equal to like 1 times 10 to the minus 3, but R1 is, I don't know, equal to like 50. Okay. If you were to calculate the R effective of this parallel system, 1 second, let me make sure this is loading too. That would be equal to 1 over 50 plus 1 over 1 times 10 to the minus 3, all to the negative 1, okay? So then this ends up equaling 0.02 plus 1,000, right? All to the negative 1. And so that's the same thing as 1 over 1,000 plus 0.02, which is very small, right? It's basically 1 times 10 to the minus 3. So what you see is that if you have a very low resistance resistor in a parallel circuit, that resistor basically defines the resistance of the component together, of the whole parallel block. So as long as you keep this thing very low, that's not going to affect the current of the system before we started measuring current. And also, it's going to ensure that the galvanometer only gets a small amount of current to move the needle. So it's a twofold effect. It prevents you from disturbing the system you're measuring, and it also helps you to not like break your meter. Because if you run too much current through this thing will melt. They're very sensitive. So yeah, so that's why ammeters run in series. Okay, ammeters run in series. All right. Now let's talk about voltmeters and how we use a voltmeter to measure things. Okay. Let me grab all this. So. Okay. So we say, and let's use a different color for voltage. Let's use blue. Okay. To measure voltage, you place a voltmeter or a voltmeter in parallel with what you are trying to measure the voltage of. And because of this, voltmeters have very high internal resistance. So voltmeters have very high internal resistance. So remember that ammeters have very low, I should say this is internal resistance. Sorry. Internal. Oh, you're good. We're doing circuits, Aleph. We're doing ammeters and ohmmeters. So ammeters have very low internal resistance, and that therefore when they're placed in series, they don't really affect the circuit very much. Voltmeters have very high internal resistance because they're placed in parallel. So let's again consider like what happens when you have things in parallel. Let me move this over. Will you do logic gates? Not in this class. That's a great thing for like a double E class maybe. And that involves transistors, Aleph, to do logic gates. We'd have to get into like diodes and other things. Yeah. Oh. Okay, so what happens is let's say for instance I want to measure the voltage across this device, okay? What I would do is I would then place a voltmeter in parallel with this circuit, okay? And that's the same thing as this. Okay, so let's try to like explain like why that is. Let me see. How did I do this? Yeah, I did a picture like that. Okay. Okay, so we're going to think about doing something like this. I could probably just copy my thing here. right? And that's what the galvanometer is going to measure. Okay. Ethan, I'm teaching physics today, dude. This is physics. Okay, so what happens here is that this is now very high. And what that does is we know that if, for instance, this is a very high voltage, or very high resistance, sorry, that means that not much current is going to run through it, right? Current would rather go through this than go through this, because this is more difficult. And again, we explained that kind of like down here, right? If you have higher resistance, you end up having less current going through that leg. So in this case, we have current going through the component, and we also have current going through our voltmeter that we're measuring. And because this is in parallel, and because this has very high resistance, there's not going to be much current running through it. Okay. And that's going to ensure that our meter doesn't like fly off the rails and stuff, right? Yeah. Okay. So then, but what we do know, right, is that the amount of current running through this is going to be proportional to whatever voltage is going across this. Because remember that the voltage from here, V plus to V minus, is the same voltage as V plus to V minus here. So when you measure the amount of current going through here, which is very low, that corresponds to what the voltage is through here. Because remember that V is equal to IR. Or we say like I is equal to V over R, right? So if I see more current through my galvanometer, then I know that my voltage must be greater here. And because this is a very high resistance, that ensures that that current is very low. And also because this is in parallel and has a very high resistance, it doesn't really affect the overall circuit. Because, again, let's say, for instance, this now has, let's say, for example, this has a resistance of 1 times 10 to the 6 ohms. Let's say it's a mega ohm is on your voltmeter, okay? Now, if you were to consider this whole thing as a parallel component, right, you would have that, okay, so R1 new, which is like the effective like R1 here, would be equal to 1 over 1 times 10 to the 6 plus 1 over, I guess, 5, right, all to the negative 1. This ends up being basically 0, right? 1 divided by 1,000,000 is very, very small. Okay, so this is basically 0. And so you get, okay, cool, R1 new is equal to 1 over 5 to the negative 1, which is just equal to my 5 that I started with. So I guess in a more generic sense, you could say this. R1. This is basically 0, so you get 1 over R1 to the negative 1, and so then it just basically equals R1. So this is a cool way that because the voltmeter has a very high internal resistance, and because it's connected in parallel, it doesn't affect the circuit. This is the key thing. When you're using voltmeters and ammeters to measure stuff, you don't want to be affecting what's already happening there, because then you don't know what you're measuring, if it's the effect of you poking it, or if it's yeah, no, you're cool. Yeah, exactly. Yeah. So a key thing, right, is that the galvanometer, the meter, can only take small currents, okay? So in the case of the ammeter, right, the galvanometer is in parallel with a resistor that's part of the ammeter. Here, this whole thing is like the ammeter, right? And because this is very, very low, not much current goes here because more current wants to go this way. In a voltmeter, okay, which is just this device, this is placed in parallel. And because this resistance is very high, not much current runs through the voltmeter. A lot of current just runs through the regular resistor that you're trying to measure the voltage across. And the other reason for this is if this is a very high resistance and in parallel, it won't affect the overall resistance of the whole system because of this. Yeah, since they're in parallel, they measure the same voltage. Exactly. Yeah, this is just calibrated in that, like, it knows this is, like, super high. So the current's going to be very low, but the range of the current still corresponds to the same range of the voltage. In the case of the ammeter, you want a lot of current to run through the ammeter. Like, current runs really easily through an ammeter because you're measuring current. You don't want to disturb current. With a voltmeter, you don't lose much voltage across it. So in this case, right, you don't lose much current because not very much current is being deviated to here, and it's in series. With a voltmeter, you don't want to lose much voltage. And you do that because that's in parallel with this, but this has such a high resistance that it doesn't draw much current, and it doesn't change the overall resistance of the system. Yeah. The key thing you want to know is that voltmeters need to be placed in parallel, ammeters need to be placed in series. Yeah, and they blow the fuse, exactly. Yeah. And yeah, let's watch what happens if you do that. Right? Yeah, that's the next point I was going to get to. Thanks, JD. Exactly. Where's my circuit? Where's my circuit? Come here. Right. Yeah, what happens if you do a bad job, right? And plug the wrong thing in. So, like, if you done goof. So, let's say, for instance, let's say, for instance, you put the voltmeter in line in series, which I don't know what you're measuring the voltage across here. Actually, technically, yeah, there is no difference in voltage. This is, again, something that has a very, very high internal resistance. So what this does is this ends up sucking up most of the current. And most of the voltage as well. All the voltage now only cares about this thing because this thing has a very high resistance. And right, V equals IR. So if you have a very high resistance, you're not going to have very much current flowing in the system anyways, but almost all of that current will be kind of deviated to this thing. And it would just end up like messing up your circuit. But yeah, if you measure voltage with an ammeter, that's when you can blow things up, right? So you don't actually, I don't think you blow anything up if you hook up a voltmeter in series. I think it just doesn't really work. I mean, yeah, because this resistor here is going to drop almost all the current. Yeah. So your galvanometer will still be safe, but you will end up basically blocking your entire circuit because this would be like R is equal to, like, I don't know, let's say basically like infinity. And now these things get zero current going to them because it all just gets dumped in this. But if, for instance, you hooked up an ammeter like a voltmeter, like in parallel, then you do some bad things. Okay. So if you hook up an ammeter in parallel, okay, remember that this has a very low resistance. So all of the current now bypasses this and will go through here. Okay? And what that means for your ammeter, let's get a picture of the ammeter. Where is it? Pull this down. Nope. So voltmeter In series, we'll basically like shut down the circuit. It acts like a massive block, is what it does. Whereas an ammeter in parallel will blow a fuse. And the reason for that is, remember that this resistance, right, is very low. This resistance is very high. So now what happens is that all of the current will bypass this and will just run straight through here. And so you end up like running way too much current. Dr. Gold makes me blow a fuse. What's up, Penn Center? Good to see you, dude. Yeah, this is very low. So what ends up happening, yeah, you just have like all the current just bypasses this, and then it'll run right through the ammeter, and that will end up melting some wires, which is not good. Yeah. Especially depending on like whatever the resistances are here. Yeah. So ammeters in parallel will blow fuse because you have too much current. Yeah, been a long time. Nice, Pen. Yeah, this is my last week teaching this physics course. It's actually my last official new content lecture. They got a final on Friday. We'll reroute through the ammeter. Yeah. So yeah, don't put voltmeters in series. Don't put ammeters in parallel. You end up just drawing all of it. Yeah. Oh, thanks for the sub. Appreciate you, Pen. Okay. Let's see. I think we have some clicker questions related to this stuff. Let's see. There we go. Okay. First question is like pretty basic. Good. Let's get the answer choices. Okay. So, first question is, when measuring current through a resistor in a simple DC circuit, everything we've been doing so far is simple DC circuits, an ideal ammeter should be connected. We know that's in series, right? Don't connect it in parallel. Bad things happen. And should have low internal resistance, right? Because if it has high internal resistance, it's going to end up affecting the circuit if it's in series. What's up, Obi? Yeah. So correct answer for this one is B. Go check that out. Nice. All right, let's see what the next question is. Ooh. And then let's get this. Okay, the next question says, a student uses a real voltmeter, which has an internal resistance, to measure the voltage across a resistor in a circuit and finds that the reading is lower than the true no-load voltage. So they mean like when they don't have a voltmeter on it. Which explanation is correct? Okay. So let's remember, right, voltmeters have a lot of high resistance. The voltmeter draws so much current that the battery's internal resistance causes a voltage drop. I don't know what that means. Or are they saying the voltmeter would affect the voltage source? I don't think so. So they're saying, for instance, if you have, let's say we're measuring the resistance over R1, and you have a voltmeter, right? That's here. Okay, so they're saying that this would draw so much current that the battery's internal resistance, I don't think so. This is not affecting what's happening here, so this is wrong. The voltmeter adds series resistance to the circuit. Well, that's not right either. If you're doing a good job, voltmeters should always be connected in parallel, so this isn't correct. The voltmeter's internal resistance is negligible. Well, the voltmeter's internal resistance is huge. Voltmeter should have very high internal resistances because you don't want current to bypass this resistor. And that would effectively lower the effective resistance of this, right? Which would, I guess, well, let me think about that. That would then increase the current that's being measured. So yeah, this is not right either. Oh, so it must be choice C, but let's see why. The finite RV of the voltimeter in parallel with R changes the equivalent resistance, altering the voltage division. So that is true. There is some finite voltage here. Some finite voltage drop. Because there is some resistance. We say the resistance is usually very high. Again, with what we said, where was it? Here, right? If you want to calculate the new effective resistance of putting a parallel voltmeter with high resistance in, right? This should basically go to 0 and not really affect what the resistance, the overall effective resistance of the whole thing is. It should be the same as just the resistance of what you're measuring. But if that amount is not very high, let's say it's like kind of low and whatnot, that is still going to then create a drop in the overall resistance here. And if there's a drop in the overall resistance, let's think about it. Drop in resistance, you would technically get more current running through it, and then V equals IR. Oh, voltage would stay the same. But you would see less voltage drop across the resistor then. Yeah. And so that's why you would measure a lower voltage. Yeah, the reading is lower than the true voltage. Yes, that's because the resistance here, RV, is like not high enough to be negligible. Because let's again remember, for things in series, they have the same current. They divide voltage, whereby something with a higher resistance has a higher voltage across it. For things in parallel, they have the same voltage, and they divide current, where lower resistance means higher current. So, if this voltmeter does not have a high enough resistance that it now starts to affect the overall resistance of these two things in parallel, that will drop the resistance, the overall resistance of this system. And if that drops the overall resistance, right, that's lower R, which means that you would measure a lower voltage across the device. Yeah. Oh, you know that pen? Yeah, series and parallel? Yeah. It's cool. Yeah. Circuits are great. I love circuits. Anyway, so correct answer for that one is C. Nice. Okay, cool. Let's look at, just to wrap this chapter up, there's some cool practical applications of why we the hazards of electrical safety. Yeah, I love this. Yeah, this is great. So yeah, so there are thermal hazards, right? Okay, so the classic example, yeah, is what so like we're gonna say like hazards of electricity, because electricity can like do bad things to you. Hazards of electricity. So the first thing here is thermal hazards, which is like heat. Okay. And that has to do, right? Heat, thermal, whatever this is related to power. And let's remember that power is equal to I squared R, right? Okay. So in the case of what we call like a short circuit, which let's say, for instance, you have a regular battery. Let's say you have let's say we have a 10-volt battery here, and it's going through some device that has let's say like 10 ohms of resistance on it. It could be a light bulb, could be a toaster oven, I don't care. Like some sort of load that it takes to power it, okay? From V equals IR, right, we know here that I would be equal to 1 amp, okay? So if I wanted to figure out the power going through this thing, right, so the power would just be equal to I squared, so that would be 1 squared times R, which in that case is 10. So that's equal to 10 watts. Cool. 10 watts is not that bad. Yeah, 10 watts, great. Not very much heat coming from 10 watts. Okay, let's say instead, though, that something breaks here. Okay, and what happens is that there is a short circuit. So a short circuit means that instead of the power running through your device, it skips it, and it ends up just doing this. And let's say, for instance, there's an effective resistance here that's very low. Because, again, even just blank wire has resistance to it, but it's very low resistance. But let's say this resistance is equal to 1 times 10 to the minus 3 ohms. So let's say it's equal to a milliohm, okay? Now let's look at what the new circuit would be. Okay, so now I don't really care about this. Let's say this thing breaks, right? And then this just like shorts across it. All of the current is going to run through here. So if we want to do V equals IR, I now have, 10 is equal to I times 1 times 10 to the minus 3. This is my new R. This is so this is short circuit. Okay. Now when I solve for I here, this becomes 10 divided by 10 to the minus 3. This becomes I is equal to 10,000 amps. Right? This is huge. All right, let me do it in the same color. So here, I would be equal to 10,000 amps if you were to divide this over. And if we were to do the power, right, that's going to equal 1 times 10 to the 4 squared times my resistance, which in this case is 1 times 10 to the minus 3. And so that's 10 to the minus 8, 10 to the minus 3, so that's 1 times 10 to the 5. So that's that's a lot. That's 100,000 watts. Okay? So now instead of your device burning through 10 watts of energy, it would burn through 100,000 watts. Now, this is not realistic because wires would melt, fuses would flip, lots of things would break before you would actually be allowed to draw 100,000 watts for any amount of time through your circuit. But this is an example of how a short circuit, when you accidentally like get the terminals to really just connect to each other, causes a lot of problems. And this is a hazard. This is heat, and this is called a fire. So anytime you see like fires being caused from like power lines or electrical problems, it's because the normal load they were going through no longer exists, and the terminals of the batteries were able to basically just connect to each other. And that just generates an insane amount of heat through whatever is connecting those two terminals. Yeah. You can do this too. I don't actually don't take this. I'm not recommending this. So this is off the record. But if you ever take like a 9-volt battery and like put it on your tongue, we did this in my school. I think this is probably banned now these days. But you actually do like end up like short circuiting a battery through your tongue, and it will cause your tongue to like sizzle and like do things. But don't do it. But that's that's another equivalent of a short circuit, because what you're doing is you're connecting the terminals of these batteries to each other, and then so a lot of current is running through a very low resistance, which creates a big dump of power. Yeah. So short circuits, those are bad. That's also why you just eat the Tide Pods instead. That's also why you should be very careful, right? When you have like two ends of a battery, that they don't touch, because then the current runs straight through whatever is connecting those two terminals, and usually that's a very low resistance thing, and that'll create a bunch of watts going through it. Yeah. Oh, okay. You can also have shock hazards. Yeah, so this is like grounding things. This is actually kind of cool. It's a good explanation. You guys ever wondered why your appliances have either like 2 prongs or 3 prongs? It's usually annoying, right, to have the third prong. You're like, man, this thing sucks. Like, I don't want the third prong because it doesn't fit into all my sockets. That's the difference between what's called like a grounded circuit. Yeah, okay, so here we're going to talk about like grounded circuits. And so the example for this is, let me see, like 2-prong versus 3-prong plug. Yeah, here we go. Okay. So yeah, this extra prong here is annoying sometimes, right? Because it doesn't fit into whatever your power adapter is. There's a safety reason for this, okay? So let's say, for instance, that you have, well, I want like a better picture of this. I don't want someone like touching where's like someone touching a, one sec. I want like a toaster or something. One sec. Okay, whatever. Yeah, pretend you have like some device here, okay? And a short circuit occurs, and you are touching it, okay? What ends up happening is, if for whatever reason the circuit inside starts connecting to the case of whatever you're touching, that current will then try to flow through you into the ground. So it's usually like, it's some high voltage, right? So this is a big plus V. And remember that electricity likes to run from high potential to low potential. So it ends up going through your body to the ground, and you get shocked. So when you have something that doesn't have another ground for it, you end up getting shocked. In the case where something does have this third ground here, here's what happens, is that whatever the device is, they have another wire connecting to the chassis of whatever the thing is. So you can think like the outside of a toaster, or the handle of a blow dryer or whatnot. And that connects to another wire in the circuit that goes to ground. So in this case, if for whatever reason your device malfunctions and the power source starts getting connected to the chassis, to like the outside of the thing, now the electricity doesn't want to go through you, because you're relatively high resistance compared to just going through the third pin here and going back into the wall. So this third pin here is usually connected to the outside of your appliance. And what it does is it provides a path for electricity to return instead of going through you if it's accidentally getting connected to the chassis. Yes. So Yeah, next time, usually you will see this on high-powered things because it would be really bad if it malfunctioned and the power went through you. You would get a really nasty shock. These are usually for like low-power devices where it's not really that risky. But for things that are high-powered and they have 3 prongs, don't go getting what is it? These things. Don't do this. You'll be tempted with these little adapters. They take like a 3-prong to a 2-prong. That 3rd prong is there for a reason. It's to protect you from, shocking yourself too bad if for whatever reason the device starts malfunctioning. But for low power things, it's not really that much of a risk. So yeah, look, this man's like really sad. He's not having a good time.
No.
Okay. Anyways, all right, sorry, I kept you guys a little bit after time. All right, awesome. So that's circuits. That is all the material we're going to cover in this summer session. Tomorrow and the day after tomorrow, I will do more review stuff to get you guys ready for the final on Friday. So I hope you enjoyed this. It was cool. Come by office hours today. I have office hours today starting at 4 o'clock. I'll probably go till like 6 or 7. So yeah. Hope you guys enjoy. Come by office hours. Otherwise, come by tomorrow for a lecture. Nothing's graded, but it'll still be informative, and we'll go over some review stuff for the final. Yes. Awesome. Great. Enjoy the rest of your Tuesday, guys. I will see you either later today or tomorrow. Peace.